Welcome to problem solving session for the course Linear Algebra. I am Siddhi Balgambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 9, that is problems related to complement of a subspace in vector space, direct sum and quotient spaces. So let us start with our first question. So UX be subspace of R4, that is x-axis, and UZ denotes the z-axis in R4, where the coordinates of R4 are denoted by x, y, z, w. So UX is a x-axis in R4 and UZ is a z-axis in R4. And so find basis of the quotient spaces R4 by UX intersection UZ. R4 quotiented by UX and R4 quotiented by UX plus UZ, and we have to find what are their dimensions, and then we have to compute the same for XY plane, UXY, and ZW plane, UZW in R4. So what this UX is, so UX is basically this subspace in R4. This is generated by this is how they are looking at it. So where X varies in R like this. And similarly, so this UX intersection UZ is intersection of these two spaces. Let me write UZ as well. 0, 0, Z, 0 in R4. Again, where Z varies in, or if you want, just don't take these names here. C0, where A and C belongs to R. Okay, so this is what we have the information about. So this is UX, this is UZ, both are subspaces, and we have to find the basis of this R4 quotiented by UX intersection UZ, R4 quotiented by UX, and this is plus. So we know intersection of two subspaces is again a subspace, and UX plus UZ is a subspace generated by both these. Okay, so we have to find that. Let us start with it. Okay, so if we call this, so this is basically R100. If we express it in terms of, for example, the way we use, like K is a vector space generated by, so let me just write x1 to xn, then we write V is equal to kx1 plus kx2 plus kxn and so on. Okay, so we can also write direct sum, that's not a problem, but yeah, I hope you got the idea. So similarly, I'm just writing this UZ since it is generated by only one element. Okay, so yeah. Okay, so these are the subspaces, and let us calculate the So we call this as E1. This so we let us denote. We denote the E1 is equal to 100. Just this is just for the for the sake of this is basically XYZW as denoted in the question and nothing else. So yeah, but even E2, E3, E4 is the general way where we that's how we denote basis and Rn in for standard basis. So yeah, we have this. So let us start with the intersection. So we have to do this for intersection Ux and Ux plus UZ. Okay, so I think yeah, that's not really matter, but okay, let us do this and then we'll see. So intersection. So for R quotiented by R4 quotiented by UX intersection UZ. So what is UX intersection UZ first of all? This is R1000 intersection R0010. And we so what we okay, so this is so if something so if some U belongs to UX intersection UZ, this implies U is of the form X000 for some X in R, and U is also of the form 00Z0 where Z is in R is of this form. Oh, okay. So this implies X is 0 and Z is 0. Okay. So therefore, thus we get UX intersection UZ at just 0 element. So therefore, dimension of UX intersection UZ is 0. So therefore, this R4 quotiented by UX intersection UZ will be just isomorphic to R4 here. Okay, and dimension. So we have to find basis, and we have to find basis, dimension, and we have to find that for this XY plane and ZW plane. So for now we, oh, sorry, yeah. So UX intersection UZ is 0, and these R4 quotiented by UX UZ will be R4. So in general, so basis we can take. So this is actually R4 quotiented by just 0. This is isomorphic to R4. So if you want to find the basis, so and then dimension, we know how the dimension for quotient is. So dimension of V quotient U is dimension of V minus dimension of U. I hope you know this. So we will be using the same. So this will be dimension of R4 minus dimension of 0, which is anyway 0. So this will be 4 minus 0, so 4. And the basis will be here, will be this E1 plus 0, E2 plus 0. And this is why we wrote those, and E4 plus 0. So we know E4, I mean, I hope you know what this is. This is 1000 plus 0. This is 0100 plus 0. Here it is 0010 plus 0, and this is 0001. Okay, so we have this with us. So this was it for first our U x intersection uz. Now second we do this for just ux. Ux we know what it is for ux. So ux is just r e1 or r1000. So dimension of dimension of again r4 quotiented by ux will be, so this is dimension of ux is just one, right? Because it is generated by only one element e1 here. So ux is dimension of ux is 1, so dimension of r mod ux will be dimension of r4 minus dimension of ux is equal to 4 minus 1, and that is 3. So 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 for so we have the whole of dimension. So dimension of r4 quotiented by ux is dimension of r4 minus dimension of ux, so which is 4 minus 3 plus 1. And for basis, what we do is we consider the quotient map. No, I have only one. I have one, but I have to. Now my speed is more, but now. So sorry for that. And for basis, we consider the quotient map pi from R4 to R4 quotiented by UX, such that okay, pi of V is V plus UX. I hope you know what this means. And so we if we take a complement of UX in R4 is the subspace spanned by E2, E3, E4. The YZW plane, Y del W space. Thus, a basis for R4 quotiented by UX is EU2 plus UX, comma E3 plus UX, comma E4 plus UX. Okay, and yeah, because at the end, what we need is elements. So in R4 quotiented by UX, everything in UX becomes 0, and rest rest elements is what gives us the non-zero elements in the subspace. Okay, so now, so we have dimension here, it is 3, and it is generated by E2 plus UX, E3 plus UX, and E4 plus UX. Okay, and that's it. And now for the third part, that is for R4 quotiented by UX plus UZ. Okay, so UX plus UZ is span E1 comma E3, and so dimension of UX plus UZ is 2, and therefore we have the dimension for quotient as dimension of R4 quotiented by UX plus UZ is equal to dimension of R4 minus dimension of this UX plus UZ. So this becomes 4 minus 2, that is 2. So dimension of R4 quotiented by ux plus uz is 1, and a complement of ux. Oh, and note that the complement ux plus uz in R4 is spanned by E2 and E4. Okay, so what we are doing here is, so understand that the complement of a subspace in a vector space is a different thing. It's not just a set complement. It is a complement as a vector space. So when we say, so understand this, that uh, let let V be a vector space over K, and U be a subspace of subspace of V. Then the complement of U in V. So this is not just basic set complement. They are saying the complement of U in V. This is the subspace U dash such that V is U direct sum U dash. Okay, so as a subspace, so this is like subspace complement of U in U dash, because U intersection U dash will be, now since V is a direct sum of U and U dash, then U intersection V dash will only be element generated by will only have zero element. Okay, so this is what this complement of U in V means. Okay, so this U dash is not just a set uh, that is sitting in the complement of V. It is also of subspace. It is something more than the normal set complement which we take in general. Okay, so this is not set theoretic. I mean, it is set theoretic in some sense, but it has more meaning attached to it. Okay, so both are complements of each other here. That U is also a complement of U dash in V. Okay, so that's what we are doing here. So complement of ux plus uz in R4 is spanned by E2 and E4. So that is because elements here are of this kind, uh, C0, and elements spanned by this E2 and E4 will be of this kind. Okay, and that's why the basis of R4 quotiented by this ux plus uz will be, just a second, yeah, it will be this E2 plus this ux plus uz, comma E4 plus ux plus uz. I hope that is okay. Okay, and yes, that's it. And now we are going to a second part, that is we have to find this for xy plane and zw plane. So for xy plane, it is, so for uxy. So understand that uxy, that is xy plane, uxy, that is xy plane, it is generated by elements of this form: a comma b comma 0 such that a comma b are in R. So this is basically ux plus uy. Okay, and so a dimension of this. So this is generated by, if you want to write this, it is generated by a1. Okay, so let me write this completely, such that AB in R. Okay, And that's it. And then so dimension, so ux y is the span of, so this was my e1 and e2 if you remember. So it is span of e1 and e2. So dimension of this uxy is 2. This is what we have. Then dimension, so therefore dimension of R4 quotiented by uxy will be again dimension of R4 minus dimension of uxy, that is 4 minus 2, and that gives me 2. Okay, and that's it. And again, like we did for this ux uz, so this was basically uxz plane. Okay, just this one, not this one, this one. So this is uxz plane. This is uxz, that is xz plane. What is the question now? And similarly, if we do for this uxz plane, yeah, so and again the complement of uxy. So complement of uxy in R4 is a span of E3 and E4. So therefore basis of R4 by uxy will be this E3 plus uxy plus E4 plus, sorry, E3 plus E, and this uxy. Similarly for, so you can immediately understand that for u uzw is, sorry, is okay, sir. For uzw it is, no, it's open. For uzw it is, again it is span of, this is span, so uzw is span of E3 and E4, and complement of, yeah, the complement of uzw in R4 is generated by, it's span of, it's spanned by E1 E2. So yeah, so therefore the base, so the basis, so dimension of R4, and so dimension of uzw is 2. Dimension of R4 quotiented by uzw will be dimension of R4 minus dimension of uzw, that is 4 minus 2, that is 2. And again we have this basis of R4 quotient, not basis, it is basis of R4 by uzw is generated by E1 plus UZW plus, comma, E2 plus UZW. So I hope you understand what is going on. So what we are asked here is to just calculate the dimension and basis of these spaces here, this one and this XY plane and ZW plane. So we did that. So what we did was we first found the basis of given space. So for example, if we want to find um, basis and dimension for R4 quotiented by W in this case, so we first find the basis for W, and then so once we have the basis, we will have the whole of dimension. Then we take complement of that vector space in R4. So what that means, so that is different than the normal complement which we have in set theory. So when we say a complement of a subspace in a vector space, it means it is subspace U dash such that V can be written as direct sum of U and that subspace. So we say that U dash is a complement of a subspace U in V if V is a direct sum of U and U dash. Okay. And their intersection will be 0. So in normal set theoretic complement, if we have some set and if we take the complement of that set in our universal set, then the intersection is empty. But the complement of a subspace in a vector space is something different. We say that a subspace is a complement of another subspace if their dimension, their direct sum gives us the whole space. Okay, so that is what complement of a subspace means. So when we have to talk about the basis of a quotient, what we do is we first find the basis of a given subspace, take the complement of that subspace, the vector space complement, and whatever the basis of that complement is, plus so the coset generated, so the corresponding cosets will give me the basis for quotient. So for example, here for UXY, um, this, so let me write again with something. So for UXY, basis, it is span of E1 and E2. So by E1, by EI, I mean 0, 0. Sorry, let me write. So E1 is just 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3 is 0, 0, 1, 0. And E4 is 0, 0, 0, 1, which we had already denoted. And so it is span of this, and so we take vector space complement of UXY, which will be so complement of this. So here this UXY complement will be span of E3, E4, right? Because this is what is left now. We can take any different spaces here, bases here, but E3, E4 is a easier candidate. And the corresponding cosets will give me, so corresponding to this E3, E4, I will get the vector subspace of this UXY and not ZW, okay? So I hope you understand how we are doing this. We did the same for ZW. So ZW is a span of E3, E4. Complement of ZW will be E2, E3. So the quotient, basis of the quotient R4 by UZW will be this E1Z plus coset E1 plus UZW and E2 plus UZW. That's it. And similarly, and we can further. So for addition of these two spaces, yeah, so R4, now we have to do this for UXY plus UZW. So note that this UXY plus UZW is whole R4, okay? So because this is generated by one E1, E2, this is generated by E3, E4, not equal to. So the whole is, so collectively they form basis for R4. So UXY plus UZW is R4, and the dimension of this UXY plus UZW is 4. Okay, so therefore dimension of their quotient R4 quotiented by uxy plus uzw will be dimension of this R4 minus dimension of uxy plus uzw, but this will be 4 minus 4, so that is 0. So therefore this R4 by uxy plus uzw is essentially R4 quotiented by R4, and that is just 0. Okay, so that if you want to be more precise, it is just 0 plus R4. And so the basis could be, if you want, you can just take 0 plus R4 or the empty set, does not matter. So, and I hope you know how the empty set is uh, basis for subspace, zero subspace, because so in general, if you want to look at the definition of basis, we can look at it this way, that uh, it is, so we say that E generates space. So span of E is actually intersection of all subspaces U such that E belongs to U. E is subspace. E contains U, where U is a subspace. Okay, and so if you want to talk about span of empty set, so that is, it will be intersection of all subspaces where empty set is subset of U, where U is a subspace of V of V. And since subspaces are non-empty space subsets, because 0 belongs there always, each such subspace of V will have 0 in it. So, sorry. So that will give me 0 as span of empty set. Okay, and yeah, so for vector spaces, so therefore basis of R4 quotiented by uxy plus uzw is empty. Empty set. Or I mean, I hope you got the idea what we are trying to say here. Okay, and yes, let me think. Can we say that 0 is generated by 0? I don't think, right? Because if I take a non-zero, then a into 0 will be 0. And this is non-linear combination of a 0 which is giving me 0. So by that sense, we can not say that 0 as a basis of a vector space. But we can also take it. I mean, it depends on what convention you are using. Okay, but yeah, I hope you got the idea that this will be, so this is 0 plus R4 and it is generated by empty set as okay. So if there are any doubts, please let me know, or we can then move to next question. Okay, and the second question is, yeah, let A be this matrix 1 2 minus 1 1 3 minus 1 5 12 minus 5, and let L of epsilon naught be okay. So this, I hope you remember the notation here, is the solution space of the homogeneous linear system defined by matrix A. Okay, so I hope so. This is so L E naught is all those x in R3 such that AX is a 0. So this is what this means. Okay, so this is solution space of homogeneous linear system. And yeah, that's the given thing. And we have to now find the R basis of the quotient space R3 quotiented by L epsilon naught. And they are asking like what is the dimension of R3 quotiented by L epsilon naught. Okay, these are the questions which we have to answer. So again, so since this is the question about L epsilon naught, we have to find all those x in R3 such that AX is a 0. So we have to find this. And so how to find that? We have various methods. So we can do this. This is 1, 2, minus 1, 1, 3, minus 1, 5, 12, minus 5. And x, if I take x, y, z is equal to 0, 0, 0. So we will do row operations, arrive at row echelon form, and we'll try to find the solution, and that will generate my L epsilon naught. Okay. And so if we do R2 R2 is R2 minus R1, and R3 has R3 minus 5 R1. That will give me 1, 2 minus 1 as it is, 0 minus R1, so 1, 0. And here I get 5, sorry, 0, and we are doing 5, so 2, and 0 again, and x, y, z, 0, 0, 0. And if I do R2, sorry, R1 is equal to R1 minus 2 R2, and R3 is equal to again R3 minus 2 R2. I will get this, right? Minus 1, 0, 0, and this xyz, and 0, 0, 0. So I get x plus x minus z as 0 and y as a 0. So this implies x is equal to z. So my L epsilon naught becomes x 0, and so if I want to write z is equal to x, does not change, and x, because z is x in R3 such that x is in R. So this becomes x10101 in R3 such that x is in R. Okay, so L epsilon naught then is R101, that is span of this element 101. And now what, when we have to find the complement of this, so understand that we have to find quotient space and dimension of it. So to find the quotient space, we have to take the complement of this subspace in R3, and whatever basis we get, the corresponding cosets will be basis of the quotient space, which we want. Okay, so what will be the complement of this? So complement of, so understand this thing that, okay, so these are remarks or notes, whatever, that if U has basis U subspace of V, U has a basis B is equal to B1 to BK. Okay, then we can extend this basis B to form a basis of V, right? And suppose this is B dash B1 to BK as it is, and this BK plus 1 to BN. I mean, I'm assuming just for the sake of simplicity that it is finite dimensional. It need not be finite dimensional, but yeah, if this is basis of V, then this U dash will be span of this BK plus 1 to Bn, and V will be this U plus U dash. Okay, we can have this. We can, I mean, we can obtain such basis of V. Okay, and that's what, and so this is how we get complement of subspace in a vector space. And so that's what we will do. So we will try to extend this element to the basis of R3. So if we add, so R3 we know is of dimension 3, is a dimension 3 subspace. So we need two more elements in R3 which are linearly independent to this element, and that will form the complement of this L epsilon naught here. So, and we can choose any element we want, and we can simply choose these two. It won't affect, it won't change anything. So we can, so note that this 1 0 0 1 0 0 0 1 0 will form a basis of R3, and complement of L epsilon naught is spanned by these two elements. So if I call them E1 and E2, then it is spanned by E1 and E2, that is this 1 0 0 0 1 0. Okay, and it is not only these two. I mean, we can take, so let us finish this and then we will discuss further. So therefore the basis of, and note that here I'm not writing transpose or anything every time. I mean, you understand, right? R3 as a column and row space, I'm considering equivalent. So here it is, we are looking at it as a column, and here I'm writing them as a rows. But I hope you understand what I mean here. So yeah, so the basis of, as I said, whatever the basis of a complement is, the corresponding cosets will form, I mean, elements in the quotient will form basis for my quotient space. So the basis for this space will be this 1 0 0 plus L epsilon naught, comma 0 1 0 plus L epsilon naught. Okay, and as we know, the dimension will be 2. So dimension, anyway, the dimension we anyway had hold of, a dimension of R4 by L epsilon naught will be dimension of, oh sorry, not R4, R3. Dimension of R3 minus dimension of L epsilon naught. So anyway, this is just one element. So therefore, this span by just one element. So dimension of L epsilon naught is 1. So 3 minus 1, that is 2. And we anyway have two elements in the basis of R3 quotiented by L epsilon naught. Okay, I mean, even from here, by counting, we could have obtained the dimension of this quotient space. But yeah, whatever we are doing is correct. And yeah, one more thing I wanted to add here is again that we chose these two elements, E1 and E2. Instead of this, we could have also chosen this. I mean, it won't change anything, okay? If instead of this, I can also take the complement as complement of L epsilon naught in R3 spanned by 0, 1, 0 and 0, 0, 1. It won't change anything. And in that case, I can also have R4 quotiented by U. Sorry, not U. What is it? Yeah, L epsilon naught basis is span of this thing 0, 1, 0 plus comma plus plus L epsilon naught 0, 0, 1 plus L epsilon naught, and it won't change anything. Okay, sorry, because here if I take some element of this form, okay, some x comma y comma 0 plus this L epsilon naught here. Okay, so what does this mean? And if I take this element here, so yeah, this is x comma. What I'm trying to say is that taking these elements won't change anything. So x plus x comma y plus 0 plus L epsilon naught. And if I, so x comma y comma 0 plus I can take this element, right, from here in L epsilon naught. So let x comma minus x comma 0 comma minus x in L epsilon naught. So this will still be true, right? Because the subtraction minus x 0 minus x belongs to L epsilon naught, right? So we said that any element x plus u, so in V quotiented by u for V quotiented by u, this we say that x plus u comma y plus u in this space u V quotiented by u, we say that x plus u is equal to y plus u if and only if this x minus y belongs to u, right? So these two elements are same here, right? X comma y comma 0 plus minus x 0 minus x plus L epsilon naught. This is equal to this because this subtraction of these two elements. So if I call this A and if I call this B, so A minus B, A minus B, yeah, A minus B is my minus x 0 minus x, which anyway belongs to L epsilon naught, right? So therefore this makes sense. And if I add these elements here, I will get 0 y minus x plus L epsilon naught is equal to x comma y comma 0 plus L epsilon naught. Okay, so when I look at this element, it is also of the form of these elements here. So if so, this is of the form E2 plus L epsilon naught. This belongs to the span of and E3 plus L epsilon naught. while this belongs to the span of, let me write this properly because this is important. So if I look at this belongs to the span of E2 plus L epsilon naught, comma, E3 plus L epsilon naught. And this, if I look at it like this, this belongs to span of E1 plus L epsilon naught, comma, E2 plus L epsilon naught. And there are many more elements you can choose, whatever you want. And you can see that due to this property, this here. Yeah, this property here. Whatever you choose in quotient, it will generate the same space. Okay. And anyway, I mean, what I'm saying is, even in what we can say, even in R3, these two elements, I mean, these two sets, this is my E2, E3, and this is my E1, E2 as, yeah, E1, E2. So even in R3, these two sets look linearly independent. In the quotient, when I take in the quotient R3, in the quotient space, R3 quotiented by L epsilon naught, these two sets actually generate same subspace, same quotient space. Okay, so these two, so what I'm emphasizing here is this E2, E3 and I mean span of E2, E1, E2 and span of E2, E3 are different in R3, but when I take quotient R3, quotient space, R3 quotiented by L epsilon naught, in that quotient space, these corresponding cosets actually generate same space. Okay, so looking at basis in V and in quotients is pretty different. Okay, these two linearly independent sets actually not linear. I mean, when I'm saying linearly independent, I mean these two are generating different spaces in R3, but corresponding quotients are same space. That's what I wanted to emphasize. Yeah, that's it. And so let us, is the question done? That's what asked or anything else? Yeah, we found the R basis, and for quotient, the number, did we find the dimension? We did not, right? Yeah, we did. We find the dimension. So we found the dimension here, and the basis is this. Yeah, so we are done. So let us move to next question now. Similarly, I mean, this question, I'm just like, I won't go to detail, but I'm just, I will just quickly go to explain what it means. So if I take L epsilon naught in Kn be the solution space of a homogeneous system of m linear equations, epsilon naught, Ax is equal to 0 in n variables, so they are saying that this X transpose is X1 to Xn with the coefficient matrix A is equal to Aij in Mn K, and we have to find the basis of quotient space K and quotient L epsilon naught, and hence the dimension of K Kn quotiented by L epsilon naught over K. So what I'm saying is that to find that, what we do is we find, we will go through this question here. So what we started with A. We have this A here. Okay. Dimension of A was 2. Dimension of A is 2. So dimension of kernel, so dimension of this L epsilon naught was dimension of R3 minus dimension of this. So dimension of this was 1. Okay. So when we will be looking at the solution in Rn, the dimension will be Rn minus the, what I can say, dimension of A. Okay. And yes. So dimension of L epsilon naught then was dimension of A here. That's what we have. So what we will do, so the similar thing will be applied here. Whatever will be, so dimension, what we find is rank of A. Or if we want to look at A, we can correspond, if we try to look at it as a map. So LA is a map from R N to, yeah, RM, such that any X here goes to AX, and L epsilon naught is in fact kernel of this LA. That is all those AX such that X in Rn such that such that AX is 0, right? What it is being, LA of X is a 0, but that is AX is 0. So we know that dimension of Rn, dimension of V is dimension of image plus kernel. So this is dimension of, so what I'm saying is that dimension of L epsilon naught is dimension of, this will be rank of A, not, wait, dimension of Rn will be dimension of, yeah, we are right. Dimension of this kernel LA plus dimension of image LA, right? And this is my rank of A because image generated by LA. This is N, we know, dimension of Rn. Therefore, dimension of this kernel LA will be N minus rank of A. Okay, so that is equal to dimension of L epsilon naught. That will be N minus rank of A. And the moment I have this, I get dimension of this Rn quotiented by L epsilon naught as a dimension of Rn minus dimension of this L epsilon naught. But this we know is N minus rank A. So that is rank of A. Okay, we will have this, and whatever is happening here, if kernel is generated by, if this L epsilon naught is generated by some k elements, n minus rank k elements, its complement will anyway give me the basis. So we can't actually. So if we call this number as suppose k, then if basis of L epsilon naught is this element, suppose B1 to Bk, then this complement of L epsilon naught will be spanned by this L minus k elements, right? N minus k elements, N minus k elements. Suppose B k plus 1 to B n, right? These are k n minus k elements with such that our n is span of B1 to Bk. This is space in direct sum span of these elements Bk plus 1 comma Bn. Okay, and whatever the what I can say, whatever the complement, whatever will be the basis of complement space, the corresponding basis of this R n quotiented by L epsilon naught will be generated by this Bk plus 1 plus L epsilon naught, so on. I hope you understand what we are doing here. This is very general setup. We are not explicitly given what A here is. Okay, so this is how it will be. The dimension of L epsilon naught will be n minus rank of A. For this we are looking at this LAX as a map so that we can get hold of this using rank nullity theorem. And yeah, and this was just dimension of L epsilon naught. Okay, and I hope you got the idea what we are doing here. This rank of A, we since A, so once we start the question, A will be fixed, and we will have the hold of rank of A and what the image space is generated by, and the kernel. I mean this L epsilon naught and what the image is generated by. So once we start the question, we will have the hold of this A, and accordingly we can develop everything. If there are any doubts, please ask. Otherwise, I can move to next question. I mean, I hope you understood like what we are doing here. Okay. And the fourth question now, that let A be this 0, 1, 0, 0 in M2C, and let U be subspace in M2C, BC subspace. So we are now looking at uh, complex vector subspaces generated by A and A transpose. Okay, we will see what kind of space that is. And we find, so we are asked to find a C basis of the quotient space M2C quotiented by U, and the dimension of M2C quotiented by U. Okay, and we will do the same thing as we are doing so far. Yeah. Now we will see what if A is this 0, 1, 0, 0, A transpose is 0, 0, 1, 0. So this space, let us call this space U. Yeah, that's what they have called it. So U is generated by this element. Generated by, so this is AC plus A transpose C. Okay, and if you want to, or let me write this properly, 0, 1, 0, 0 plus B 0, 0, 1, 0 such that A comma B are in R. So this is just elements of this kind. 0, 0, A, B, 0 such that A comma B are in R. Okay, these are the kind of elements we have here. Okay, so span of U, so dimension of U is, so if, yeah, so dimension of U is 2 because it is generated by two elements. So the dimension, therefore, dimension of this M2C quotiented by U will be dimension of M2C minus dimension of U. So dimension of M2C is 4. I hope you know that. Okay, dimension of M2C is 4 over C. Okay, and over R it is 8. You can check that, but that is different thing. But yeah, we have this at least. That is 4 minus 2, so 2. And complement of U in M2C is is spanned by this, right? 1, 0, 0, 0, the diagonal elements, and hence uh, basis of this M2C, yeah, M2C quotiented by U is this 1, 0, 0, 0 plus U, comma 0, 0, 0, 1 plus U. Okay, so that's it. I mean, yeah, I hope you got what we are doing here. So in short, to find the dimension and basis, yeah, basis of a quotient, first we have to find the basis of a given space U, and then we will get hold of dimension, because dimension of U quotient V quotient U will be dimension of V minus dimension of U. So we will have the number of elements that will be there in the basis, and then we have to take the complement space. Okay, and whatever is the basis of that complement space, the corresponding elements in the quotient space will form the basis for my quotient space V quotient U. That was the main idea of whatever we solved so far. And now let's move to this next question. Yeah, question 5. Okay. Let U and W be subspaces of V with U contained in W. And if W dash is a complement of W in V, then U plus W dash quotiented by U is a complement of W quotient U in V quotient U, which is isomorphic to W dash. This is the question. So what they are saying is that if we have two subspaces U and W, and U is contained in W, then what they are saying is that if V is W direct sum W dash, then, and if U is contained in W contained in U dash, V, then what they are saying is that this U, V quotient U, this will make sense. And since W is in U, this W quotient U will make sense. And this will be direct sum of this U plus W dash quotient U, okay? I mean, we are doing this U plus W dash quotiented by U because the U is contained in W, right? So if we take W dash, which is vector subspace complement, then U won't be contained in this, right? Because if there is some element X in U, that is X belongs to such that it belongs to W dash, then this X is also in W by the given condition, and then this X will be in both W and W dash. So this this U is not contained in this W dash space. So therefore, for this quotient, this second quotient to make sense, since we are talking about, so what they are saying is if we have a direct sum in original space, we can get hold of direct sum in quotients as well. That's the crux of this question here. And but to make sense of this, the corresponding quotient of W dash here, what we do is we add this U here, because now once we have this U will be contained in U plus W dash as a subspace, okay? These are all subspaces we are talking about. Okay, so this is the question and we are trying to solve it now. Okay, and there are many. So this is the first part. This is the first part. And then they are saying that this complement of W quotient U in V quotient U will be isomorphic to W dash and so on. So we will see that as well. But this is the idea of this question, that having hold of direct sum or complements in the original space, we can have the idea about the complements in the quotient space as well. So let us start with the proof. So we first verify. So we have to show that V quotiented by U is right. This is what is asked to prove. So first we check. So to do this, we show or we check this, that V quotiented by U is at least the sum of these two elements, okay? And then we show that their intersection is 0, and then we will get hold of this. I hope this is okay, right? I mean, direct sum is essentially that. Direct sum, so, I mean, I know, yeah. And U intersection W is 0. This is what it means, okay? So instead of directly going to direct sum, what we will do is we first show that it is addition of these two sets. Sorry. And then we will show that their intersection is 0. So consider some element V plus U in this V quotient U. That's how elements of quotient sets, quotient spaces look like. And then since this V is in V and V is W direct sum W dash, we get that this V will be some W plus W dash, right? For this W in W and W dash in W double dash. Sorry. Yeah, W dash, small w dash in capital W dash. Okay. So therefore, since this is the case, this U plus U will be this W plus W dash plus U, and this is nothing but this, right? This we know. This is the definition and how addition is defined in cosets. This is what we have. And since W dash belongs to this W dash, this implies that W dash also belongs to W dash plus U plus W dash, right? Because this I can write just W dash plus 0 where 0 or 0 plus W dash. And this 0 I am considering element from U. Okay, so this is there because anyway, see, this belongs to W dash, which is anyway contained in this. Understand it like this, and it is even better. So we have hold of this. So therefore, this V plus U we can write as W plus U plus W dash plus U, where this W plus U belongs to W quotient by U, and this W dash plus U belongs to this U plus W dash quotiented by U. Is this okay? This we are getting directly from given condition, and we just have to see that this W dash plus U, I mean, to make the quotient make sense, we added this, yeah. So this W dash plus U is also, this W dash is not only an element of W dash, but it is also element of U plus W dash. That's what we noted here. And so any element here can be written as a addition of these two quotient subspaces. Now the intersection part. Okay, now we have to show. So therefore, V quotiented by U is W quotiented by U plus this U plus W dash quotiented by U. This is what, hence, this is the case, okay? And now we have to check that W quotiented by U intersection this is just this 0. That's what we have to check. So 0 means this 0 plus U in the quotient space. That's what we have to check. So suppose I take some element. Suppose X plus U belongs to intersection, this W quotiented by U intersection U plus W dash quotiented by U. Okay. So this implies that this X plus U will be some W plus U for this W in U. right? Because it is in intersection, so it belongs to both the sets. And similarly, and this x plus u will be some u plus w dash plus u for some u in u and w dash in w. That's what the definition says. Okay, and since these two are same, we get that this w plus u is u plus w dash plus u. And now so this implies that this w minus u minus w dash, this belongs to u by the definition, right? By the quotient space property. So let us denote y is equal to w minus u. Okay, and this belongs to w, right? Because u belongs to u, which is contained in w, and w belongs to w. So this y, this new element, this belongs to w. So this implies this y minus w dash belongs to u, which is also contained in w. So from here, we have this. And from here, I'm just writing this like as it is with different notation. And since u is contained in w, this is happening. Since u is contained in w. So this implies this y minus w dash is contained in this space. So this belongs to, okay? So this implies that minus w dash belongs to w, right? Because so this implies this w dash, which is equal to y minus w dash minus y. This will belongs to w since y belongs to w. So this implies that minus w dash belongs to w. Okay. So, or we can just do this. Okay. But w dash was in w dash, right? By the choice here. So w dash is in w and w dash is in w dash. This implies that this is 0, right? Since w dash belongs to w intersection w dash. And from this, once I have this, then x plus u, which was u plus w dash plus u, since w dash is 0, this x plus u will be u plus u. And this implies that x belongs to u, and hence x plus u will be just 0 in v quotient u, right? Because this will imply what? X minus u belongs to u. But since x minus u belongs to u is in u, so this will imply x is in u by the same argument which we have here. So therefore, x was in the intersection which turned out to be 0. So therefore, this w quotiented by u intersection this u plus w dash quotiented by u, this is 0. And therefore, this v by u is direct sum of these two spaces. Okay. I hope this was okay so far. Okay. And now the isomorphism part. So second part of the question is that then this is isomorphic to W dash. That's what also we have to prove, that this space here is isomorphic to W dash here. So to show now, this U plus W dash quotiented by U is isomorphic to W dash. This is what we have to show now, the remaining part. So we define this map, that phi from W dash to U plus W dash quotiented by U. Okay, and it as and we can say such that this W dash is going to W dash plus U. The simple projection in quotient. Okay, then kernel of this phi will be what? All those W dash plus U, sorry, W dash in W dash, such that W dash plus U will be, or let me write, phi of W dash, that is W dash plus U, is 0. But this imply that, so this will imply that, oops, sorry, kernel is belong, such that W dash belongs to U, right? That's the only way we can have this to be 0. Because, okay, so therefore kernel of P is all those W dash in W dash such that W dash belongs to U. So these imply this is W dash intersection U, right? But U is contained in W and W dash intersection W is 0. So this will imply that W dash intersection U will also be 0, right? Because if some element X belongs to, understand that, since if X belongs to W dash intersection U, then X belongs to W dash and X belongs to U, which also a subset of W. Then this implies that this X has to be 0 because W intersection W dash is 0. So therefore this W, I mean whatever the kernel was, turned out to be 0. So therefore kernel of P is 0. So therefore P is injective. And for surjectivity, for let this U plus W dash plus U belongs to this element U plus W dash quotiented by U. This U plus W dash plus U is W dash plus U, right? U plus W dash plus this U is W dash plus U. Because subtraction will be U, which anyway belongs to U. Okay, but this is phi of W dash, right? By definition. So therefore, for any such U plus W dash plus U, so therefore for any U plus W dash plus U in this space, P of this will be w dash plus u, that is equal to u plus w dash plus u. So therefore P is surjective, and hence phi is an isomorphism. And that's what we wanted to prove. So hence we get that this space w dash is isomorphic to u plus w dash quotiented by w dash. Is it okay? And yes, so that's it. Now let's move to next question. Yeah, yeah. No, I think this is question 6. That just a second. That let V be a K vector space. Okay, and u comma u dash be subspaces of V. Okay, so we have to show that first part, that if u is contained in u dash and u is finite codimensional, okay, finite codimensional, then u dash is also finite codimensional. So what finite codimensional means is dimension of V quotiented by U is finite. That's what what is finite dimension. Let me write it properly. Okay, so this is what we are given. So this is what finite codimensional means. And second part is that if U and U dash are finite codimensional, then U intersection U dash is also finite codimensional. This is the first part. And B is that let F from V to V be a K-linear map, and U is a finite dimensional, U is a finite codimensional. Then we have to show that first is that F U inverse U is also finite codimensional. Subspace of V. And second is if f of v is finite codimensional in V, then f of u is also finite codimensional in V. Okay, so this is what we are asked to check. So everything is codimensional. So codimensional means we are talking about quotient spaces in short. Okay, so when they are saying f inverse u is also finite codimensional subspace of V, it means V quotient f inverse u is has finite dimension, and similarly f of V. So when they are saying that f of V is a finite codimensional in V, means V quotiented by f V, that quotient space has finite dimension. Okay, so that is what is given to us, and now let us do the proof part. So the first is a part of a first, that if u contained in u dash is also u dimensional, u is finite codimensional, then u dash is also finite codimensional. That is what we have to prove. Okay, so what we will do is that let u be, wait, yeah, let u contained in u dash contained in V is what we have. And since u dash contains u, the quotient u dash u is a subspace of V quotient u. Okay, like in earlier case, when we have this w u contained in w contained in V, this w v sorry, yeah, this w quotient u was a subspace of V quotient w, if you remember properly. Because we wrote V quotient, sorry, u. We wrote that w quotient u, V quotient u was direct sum of w quotient u and u plus w dash quotient u. Okay, so that w quotient u, we can write direct sum only if they are subspaces. Okay, so this w quotient u was subspace of my original space V quotient u. So this is there, and so we have this, right? That if that is the case, then this V quotient u dash will be isomorphic to V quotient u quotiented by u dash quotient u. This I hope you know. Okay, this how we do is we define a map, and then kernel of that map becomes u dash quotient u. That's how we do it. So we define map. So how to do is that we define phi from V quotient u to V quotient u dash, and this becomes, since u is contained in u dash, this becomes isomorphism. This becomes isomorphism, and not isomorphism. This becomes a surjective map, and then therefore this V quotient u dash becomes isomorphic to V by u quotiented by u dash by u. and we can check that kernel of this map V will be this U dash quotiented by U. And how this map is defined? Okay, I did not write the definition of map. This V goes to this V plus U goes to V plus U dash. Okay, you can check this. I hope you know this. This is also called as third isomorphism theorem of vector spaces. Okay. So using this, we have this, and therefore once we write this V quotiented by U dash as quotient of these two subspaces isomorphism, then we have this. I mean, also using the rank nullity theorem on this V, we get that dimension of this V quotient U dash will be dimension of this V quotient U minus dimension of this U dash quotient U. I hope everything is clear. What is V and what is U? This we have. And now note that this is finite dimensional. Okay, that's what is given, right? U is finite codimensional. U is finite codimensional. So U is finite codimensional means this quotient V quotient U is finite dimensional. And whatever will be the I mean, this will be always greater than equal to 0, some number. And this is finite dimensional. So whatever number here, this will be some finite number, right? This will definitely be lesser than dimension of this V by U. Okay, so that will give me that this. So this implies, and so this will imply that, let me use, so this will imply that this is finite dimensional. And once I have this finite dimensional, I get U dash as finite codimensional. Is that okay? And I mean, we can also understand it like this, that since, let me write it properly, since U is finite codimensional, this implies that dimension of V quotient U is finite. This is there, and this U dash quotient U is a subspace of V quotient U. This implies that this dimension of V quotient U, sorry, U dash quotient U is less than equal to dimension of V quotient U, okay? And so anyway, this is anyway less than infinity. So this is some finite number. What I'm trying to say here is the number here on the right hand side is some finite number, and therefore this implies that dimension of this is my left RHS, and therefore this LHS dimension of V quotient U by will be strictly less than infinity. Okay, since this is finite dimensional, I get this also finite dimension, and therefore this U dash becomes, therefore U dash is a finite codimensional in V. Okay, is this okay? That's what we are asked to prove here, that U dash is a finite codimension. And how we did that? We proved that U dash is finite codimension. And yeah, understand this please, that we started with this thing. Okay, so if you don't know, try to prove this. If you don't know the proof, try to prove this, and I mean you can use this as a hint. Okay, and yes, so let us go to a second part. What is second part? That if that U and U dash are finite let me also show it here, that U and U dash are finite codimensional, then their intersection is also finite codimensional. That is the second part. So let me write the given statement, given and what we have to show for that U and U dash are finite codimensional. We have to prove that U dash U intersection U dash is finite codimensional. This is what we have to prove. Okay. So let us, we define this map P again from V to V quotient U cross V quotient U dash. Okay, this, wait, U dash is, yeah. Okay, such that any x here, it goes to this x plus U, comma, x plus U dash. And this is often called as pi of x, and this is pi dash of x. Just the notation. Because instead of writing cosets every time, we will write this. Where, okay, where this pi is from V to V quotient U, and this pi dash is from V to V quotient U dash. Okay, and so we have to find the kernel of this map. So kernel of this phi is what? This is all those x in V such that this is 0, 0, right? That phi of V is 0, 0. That is x in V such that each of this term is 0. That is pi of x is 0 and pi dash of x is 0, right? Because that's the coordinate. So this is pi of x. This is pi dash of x, right? Oh, x here. So that is x in V such that pi of x will be 0 when? When x belongs to U, right? Because this is quotient in U. And pi of x will be 0 means what? This x belongs to U dash. So therefore, this kernel of phi is all those x such that x is both U, x is in both x and U and U dash. So this becomes U intersection U dash, right? So therefore, once we have this, so therefore by second isomorphism theorem, we have that therefore P induces isomorphism on V quotient, the kernel. So kernel of this U intersection U dash isomorphic to image of V. Okay, this is right. This is, I hope you know that this, if F is from V to W, then V quotient kernel of F is isomorphic to image of F. Okay, this is what we are using here. That's it. That's what the image of phi is. I mean, I hope you understand what we are writing this. This is the kernel. This is my, I mean, the domain. This is domain. This is kernel. And this is image space. Okay. So that's what we have here. So now if we show that images of phi is a whole space, note that image of phi is a subspace of, don't even need to prove anything further. So if phi, image of phi, we know that it is subspace of this, right? So dimension of, and each of these is finite dimensional. So is subspace of this, and V quotient U comma V quotient U dash are finite dimensional. Therefore, dimension of this V quotient U cross V quotient U dash will be dimension of this V quotient U plus dimension of V quotient U dash. And each of these is less than infinity. I mean, it's some finite number. So therefore, the dimension of this cross product, not cross product, this is not cross product. I mean, this space here will be less than infinity because each, so dimension of this V quotient U cross V quotient U dash is addition of dimension of each of them. And each of these U and U dash are finite codimensional. Therefore, dimension of this V quotient U and V quotient U dash is finite. And therefore, the dimension of this space here is finite. V quotient U cross V quotient U dash. This is finite. And once we have that, so this will imply, and so image space, image of P is anyway subspace of this, sorry, is subspace of V quotient U. Okay, so therefore, dimension of this image of phi will be less than dimension of this V quotient U cross V quotient U dash, which is less than infinity. Okay. Okay. And so therefore, and this image phi is, as we saw, is isomorphic to V quotient U intersection U dash. This is finite dimensional. This implies that this V quotient U intersection U dash is finite dimensional. And hence we get that this U intersection U dash is finite codimensional. Is it okay? Okay. It was just comparing the dimension. And now I think second part is more or less similar, but it is through the image of given k-linear map. Okay, so let us do that also. We'll finish it and then we can stop. Okay, so B part first. And what is the question? The question, let us read the question again. That F is k-linear map from V to V, that is okay. And U is given finite codimensional. What we have to do prove is F inverse U is also finite codimensional subspace of V. So we have to prove that, yeah, that's what we have to prove. F inverse U is finite codimensional. That is, dimension of V quotient F inverse U is finite. And second part is FV is finite codimensional. That is, image space is finite codimensional. Then we have to prove that for subspace U, FU is a subspace of FV. So that is also finite codimensional. That's what we have to prove. So let us do the first part, that we are given F from V to V is a k-linear map. That is okay. Now consider this pi composed F from V to V quotient U. Okay, well, we know what this pi is. Pi is from V to, not V to V quotient U, such that V goes to V plus U. I hope you know this. So it's just composition map. First we are applying F and then applying. So this is essentially F going to V going to F of V plus U. Okay, because first I apply F of V, then I apply pi to it. This is what this map is. So now this kernel of this pi composed F will be all those x in U such that this, let me write properly. Pi composed F of this x is a 0, right? And that is, and this x 0 is in V quotient U, and that is this F of x plus U, right? That is pi of F of x is a 0. So that implies that F of x plus U is a 0. And this implies that my F of x must belongs to U, right? So this kernel of pi composed F is just all those x in U such that F of x belongs to U. But if that is the case, that is just F inverse of U, right? Oh, sorry, this x is in V. The map is from V. My pi composed F map is from V. Okay, so this is here. And yeah, so so again we have then this induces isomorphism between this, right? V quotient F inverse U isomorphic to image of pi composed F. This is what we have from here. But this image of pi composed F is a subspace of V quotient U, right? It is landing in this space, V quotient U. Okay. And it is given that it is I hope it is, yeah. U is finite codimensional. It is given already. Subspace of, so since U is finite codimensional, that is given. This imply that dimension of V quotient U is finite, and this imply that dimension of image of pi composed F, that will be some less than equal to dimension of this V quotient U. This is less than infinity. So this implies that this dimension of this pi composed F is some finite. It's finite, and then because of isomorphism, so this will imply that dimension of V quotient F inverse U, right? Since this V quotient F inverse U, we just prove this will be isomorphic to Im of pi composed F. Okay. Uh, since we already have this, so this implies that this F inverse U is finite codimension. This is what we wanted. Okay. And this is what we wanted. And the B part is the second part of this B is understand that this. Look at this second part, not this first part of the question, that U contained in U dash, if U is finite dimensional, the smaller one, then U dash is also finite codimensional, then U dash is also finite codimensional. Here also, no, it's the other way around. What I was thinking was that uh, since U contained in U dash, this finite codimensional implies that this finite codimensional. But here we have different thing. Note that f of U will be contained in f of V. Okay, and we are given that now this is finite codimensional, and we have to prove that this is finite codimensional. So it's like not converse, but it is something opposite of what we did here. I thought we can directly do that, but yeah, no problem. We'll do this. It won't take much time. Okay. The second part is that we have to show that given that f of V is finite codimensional, we have to show that f of U is finite codimensional. I hope that's the question. I mean, yeah, that's the question to show. This is given, and now this is to show. Okay, so now we have this f of U contained in f of V contained in V, that is there. So we know again using the same what we did in the earlier one, that know that this f of U will be isomorphic to f of V quotient f of U, this whole quotient. I hope that is right. Yeah, this is I mean something like this. This is the smallest one. So this quotiented by this, oh, this will be f of V here. We can also do this. Let me just directly write this. F quotient this will be this quotient. Let me write this. V quotient f of V f of V quotient f of U. Yeah, this is right. This is right. V quotient f of V will be isomorphic to V quotient f of U quotiented by f of V quotient f of U. This is what we have. So this will imply that dimension of f quotient V quotient f of U will be equal to dimension of V quotient f of V plus dimension of, the subtraction. This will be dimension of this. Okay, dimension of this will be dimension of this minus dimension of this, and then they are switching. Okay, to make the positive. So f of, so this will be addition of these two. Okay, so that's what we are writing here. F of v quotiented by f of u. Okay, so let me write this. If this is a, b, c, then dimension of a will be dimension of b minus dimension of c. So that's what we are doing. The dimension of b is dimension of a plus dimension of c. That's what we are doing here. And that's what it means. I hope you understood what I'm trying to do here. And since fv is f of v is finite codimensional, this implies that this implies that dimension of v quotient f of v is finite, and f, oh, this is u or v, yeah, v. Okay, and we have to now prove this, the dimension of this is finite. So to show now that, see, we have to prove that this is finite dimensional. We have that this finite dimensional, so just left to prove that this second part is, we have to prove that this is finite dimensional. So we know that this is finite dimensional. So we just have to prove that this is now finite dimensional. So that's what we will be doing here. So we have to show that dimension of f of v quotiented by f of u is finite. So we produce, we make this map f dash from v quotient u to v quotient f of u. Okay, such that this f of u plus, no, v plus u, sorry, f of v plus this is capital F of u. This makes sense, okay? And image of this is all those f of v plus capital F of u such that v belongs to v, right? That's the definition. And that is just f of v quotiented by f of u. Okay, and since f of u is contained in f of v, since u is finite codimensional, okay, we are running out of time. So this implies that image of f bar is, so this will see this is finite codimensional. This implies that p quotient u is finite dimensional. This implies that image of this will be finite dimensional. Why this is? Because note that if u1 to uk generate u, then f is from suppose u to v, or let us f is from, yeah, u to v. This is completely different thing. If u1 to uk generate u, then f of u1 to f of uk generate image, okay? Generate, okay? If this is basis, then this generate image of f. Okay, so since this is finite dimensional, this will be finite dimensional. Dimension could be same or lesser, but at least this will be finite dimensional. And therefore, Yeah. So therefore, this dimension of f of v wait, quotiented by f of u will be less than infinity. How is that the case? Yeah, image is finite dimensional. So yeah, this is the image. Image of f bar is finite dimensional. So image of f bar is finite dimensional. So, but image of f bar is finite dimensional. That means image of f bar is this thing, f of v quotient f of u. So therefore, this is finite dimensional. Therefore, f of u is finite. So we got that this is finite dimension and the whole thing is finite dimension. So therefore, dimension of v quotient f of u, which was dimension of v quotient f of v, which we know finite dimension, and we just got that this is also finite dimensional. Sorry for this. So this is both are finite dimensional. So therefore, this is finite dimensional, and therefore f of u is finite codimensional. And we are done. Okay. So yeah, that's what we had to prove. It was more or less trivial, except for understanding this part that we have to define f dash in this sense to get hold of this. Okay, and this is the image, and we use that dimension of image is always less than the dimension of domain of the map. Okay, so that's it. Then if we are anyway have passed the time. So if there are any doubts, please. Otherwise, we can end the session. Okay. So if there are no doubts, we can meet next week, same time. Yeah. Thank you.